Hello everyone. Hello and welcome for this fourth session of papers. And today we will read a new papers from Armstrong, Virding and Williams with a new name I never saw before called Dacker. So this paper is from the 1st April 1992 and its title is Implementing a Functional Language for Highly Parallel Real-Time Application. If you remember, during the last session we have seen a lot of different kind of implementation, I will say. And the first one was more about talking about Prolog. The second one was also talking a little bit about Prolog with the beginning of the Erlang syntax coming. Last week we have seen a paper talking about the first implementation of the Erlang language, particularly like the one we are using today. So in this paper, this is more a whole presentation of the JAM, Joe Abstract Machine or something like that. And I think we will have to code as well, but this paper is already offering syntax similar from the language we are using right now. So let's start it. As usual, this paper was created by the Computer Science Laboratory called LMTL Utvecklings AB. So it's a Swedish company directly linked to, I don't remember the name, Ericsson. So let's do it. Introduction. This paper describes a fast, highly portable implementation of the real-time symbolic declarative programming language Erlang. A previous paper described our investigation into the suitability of different programming languages for use in telecommunication switching software. We conclude that declarative languages are highly suitable for the implementation of such system, and identified several properties which we regarded as essential in languages for programming robust, highly concurrent real-time systems. A subsequent paper described the prototyping work which verified and enhanced these ideas. This resulted in a slow interpreter which implements a new declarative real-time programming language called Erlang. Erlang has been used internally in Ericsson for prototyping switching systems, and tens of thousands of lines of Erlang code have been written. Projects in which Erlang has been used have demonstrated at least an order of magnitude reduction in the workload of the specification programming testing cycle when compared to projects using conventional technology. The interpreter which was used to implement Erlang was, however, too slow for use in commercial application. This paper describes some of the implementation techniques used in our fast, highly portable implementation of Erlang. We present measurement of the execution speed of Erlang when used to implement a prototype control system for PIBX. Summary of the implementation. Our implementation of Erlang has been inspired by the techniques usually used to implement Prolog. Erlang code is compiled by the compiler itself written in Erlang into instruction for virtual machine. These instructions are then interpreted by an emulator. In the virtual machine, each process has its own process either stack or heap. The emulator is written in C. In the following section, we describe the virtual machine by way of examples. Note that the instruction set used here has been simplified for pedagogic reasons. Simple sequential Erlang. Consider the following function which computes the factorial of a positive integer. So this code will work, but this is the classical description of a factorial function. We refer to this function as factorial/1. The function factorial with one argument is compiled into the following instruction. Sorry. Input tests, try me. Okay, so also the factorial/1 function above has two clauses. The resulting code has one entry point at 1. We start by trying to match the first clause factorial 0, 1. Okay. Instruction on the line 2 indicates where to start trying to match the next clause, label 1 if the first clause should not match. Instruction 3 push the first, and in this case only, argument onto the top of the stack. Instruction 4 test if the top of the stack contains integer 0. If it does contain integer 0, the stack is popped. The return value of the function integer 1 is pushed onto the stack, and we returned from function 6. So this part here. Okay. If, however, instruction 4 finds something other than the integer 0 at the top of the stack, fire occurs. This results in a jump to label 1 as indicated by instruction 2. The stack is also restored as it was at instruction 2. So we have the label 1 here. Label 1 is defined here, try me else phi. Okay. The stack is also restored as it was at instruction 2. Instruction 7 indicates there are no more clauses to match if fire occurs. Any subsequent fire will cause a runtime error. Instruction 8 pushes the argument of the function on the top of the stack. 7? No? 8. Okay. Instruction 9 duplicates the top of the stack. Instruction 10 pushes integer 1 onto the top of the stack. And the instruction 11 subtracts the top of the stack from the second location on the stack. Pops the top 2 locations from the stack and pushes the result into the stack. This corresponds to the calculation of n-1. The stack now contains a copy of the argument n in the second location on n-1 on the top. Instruction 12 calls the function factorial 1 recursively. When this function returns the result of calculating factorial n-1, will be on the top of the stack on n as the next location of the stack, put there by instruction 9 above. Instruction 13, multiply this, pop them from the stack and pushes the result onto the stack, and we return from the function 14. Okay. So we are recalling this one here. And the result here will be added to the argument of the times function. Okay. Representation of data. All data objects in Erlang are represented by a word with a tag as follows. The integer 1, 2, 3, 4, for example, is represented as box. What does it mean? Tag value. Oh, okay. I think there is a small mistake here. So this representation is made here. So we have integer 1, 2, 3, 4, and an atom table index. Oh, I think this paper had some issue. The atom table index is an index in a hash table which stores the strings of ASCII characters corresponding to each atom. In the following, we represent atoms by exams of atom subscriber number as follow. Oh, the paper is quite dirty because actually this is present here. I only find this one on internet, so I found this one on internet, so I don't know if we will continue. Let's try. So far we have been able to represent all data objects in one tagged word. Such object can be stored in the stack of processes. More complex structures are stored on the heap of processes. The Erlang tuple position 2396 is stored in consecutive heap location. The first item on the heap is an object with a tag size indicating how many objects are in the tuple. How many of the subsequent heap locations contain objects in the tuple. References to this tuple, which may be stored in the stack or heap, are represented as. Oh, yeah, it says there is a really big gap between the different elements. Lists in Erlang are represented by linked list of two consecutive heap locations. The Erlang list 11, 22, 33 could thus be represented as figures on the right representing heap addresses on the stack heap of list tile of list. Yeah. That's really not the best part of this paper, I guess. Building complex structures. The following fragment of code shows how we build a tuple when calling a function. So per database will have the argument address and geometry 23 following in the second argument, and these things will be give push atom address, push atom Joe, push atom main street, push integer 23, mk333. So this here are the argument for the tuple, and call local put database 2. So this is the number of arguments present here. Instruction 1 above pushes the first argument of the call to put database 2 onto stack the atom address. Instruction 2, 3, and 4 push the 3 components of the second argument, the tuple Joe main street 23 into the stack. Instruction 5 makes the top 3 locations of the stack into a tuple. It constructs the tuple on the heap and pops the 3 components of the tuple from the stack and pushes a tagged pointer to the tuple onto the stack. Instruction 6 calls the function putDatabase. 2. When building lists, we build one head and tail pair at a time, starting from the end of the list. Consider the following call. Analyze number and the list containing 3, 4, 5. This compiles into push nil, push in 5. Oh, ready? Funny stuff. When you are doing some drivers or if you don't have these kind of things, if I remember correctly. I need to check that after. Instruction 1 and 2 push the component of the last head and tail pair of the list onto the stack. The mk-list instruction creates the head and tail pair on the heap. Pop the top 2 objects from the stack and pushes tagged list pointer to the new created pair onto the stack. Instruction 4 pushes the head of the next head and tail pair to be created into the stack. The mk-list 5 instruction will, as before, create head and tail pair on the heap. The tail element of this pair will be the newly created tagged list pointer to the last head and tail pair of the list, thus creating a linked list of pointer. Instruction 6 and 7 create the first head and tail pair of the list, leaving a tagged list pointer to this on the stack. The call to analyze number is made in instruction 8. That's a bit weird to have. Yeah. Pattern matching. In Erlang, selection is done by pattern matching. Consider a function with as 3 clauses with the following heads. Destination X, one integer, destination local, so an atom, destination remote case underscore 1, so a tuple with an atom and another one. This compiles into info test destination 1, try me else label 1, arg0, test integer, so we are switching here. Okay. The entry point of the function is at instruction 1 above. The first try to match the first clause destination X when integers X. Instruction 2 indicates where to continue if we fail to match either of the first clause. Instruction 3 pushes the argument of the function onto the stack, and instruction 4 tests if the argument is an integer. If this fails, the argument is not an integer, we proceed to instruction 5. Okay. We now try to match the clause destination local. Instruction 5 tells you to continue at label 2. If this clause doesn't match, we push the argument to the stack and test if it is atom local. If this is not the case, we proceed to instruction 8. We now try to match the last clause. Instruction 8 tells us that this is the last clause and we will have runtime failure if this clause should not match. We push the... Okay. We push the argument to the stack. Test if the argument is a tuple of size 2. If it is, we pop the stack and push the element of the tuple onto the stack. We now proceed to test if the elements are the auto, remote and case _1. That's a pretty simple structure, indeed. Variables. Variables are introduced in Erlang programs simply by naming them. Consider the following program fragment in which we unpack a tuple. This is compiled into the following code: info test var1 jeremy blah blah blah. The function var1 introduces two variables b and c. Space on the stack for those variables is reserved by instruction 3. Instruction 5 impacts the tuple contained in A and checks that it is of size 2. Instruction 7 and 8 put the component of the tuple into variable B is variable 0 and C is variable 1. Instruction 8 pushes the return values in variable 1 onto the stack. I think this is pretty obvious. You can understand that all those kind of things is working. The idea is we have the definition of the function. We are trying if this is a good description here. So one variable, we will allocate two variables and the argument argument 0 4. Okay. Impact tuple 2. So we are unpacking both of them. If it's valid, we continue. Store var to b 0. Okay. Okay. So we when we create a variable, we create probably also an index. So we are creating var0, var1. And var0 is position of the index of the variable. And when we push var directly to return from the function, we are calling push var. Okay. Processes and concurrency. So far we have just looked at sequential Erlang. Erlang is designed for use in highly concurrent real-time system and thus implements lightweight processes. Each process has its own stack, heap, and process header. The process header stores the registers of the virtual machine when the process is not executing. Processes awaiting execution are linked into a scheduler queue. Processes are scheduled on a round-robin basis. A process executes until either it consumes a time slice or until it awaits a message from other processes. Processes are scheduled on a round-robin basis. Okay. Sequential Erlang, as shown above, requires the following register in the process header. Stack. This is the start of the stack. Stack top of the stack. Heap, stop of the heap. Heap top of the heap. Program counter, pointer to the instruction currently being executed. Address file, address of the instruction to which to jump if fire occur. Okay, and stack save. This is a set to the value of stack top by try me else instruction. When fire occurs and there are other alternatives to match, we reset the stack top register to the value of stack save. Processes headers are stored in the process table. Processes are referenced by special target data object process identifier or PID. One of the process one of the things contained by a PID is the index of the process table. The following is an example of how a process could send a message to another process. So I think if you are using Erlang, you already know how it's working. So we have send, we have the PID, the references, and for example the number, I guess. This is the PID, and we are sending the message analyze followed by the number. The function send_to above sends the tuple analyze number to the PID in analyzer. This compiles to the following instruction: arg0 push atom analyze arg1 mcatable send rate. Wow, that's really short. The first argument to the function send_to is pushed onto the stack. The tuple analyzed number is created on the heap by 3, 4, and 5. This leaves the stack with a target pointer to the tuple at the top of the content of variable analyzer in the second stack location. The send instruction is now executed. A check is first made that the second stack location is a valid PID. If it is, we copy the content of the top of the stack to the heap of the process denoted by the second stack location. Now that this means copying the entire data structure. We copy the data to which it points. Thus, we never have pointers from the heap of one process into the heap of another. Okay, so if you have really big data, there is no pointer. We are just copying something and sending this data to the other process. Each process may have a queue of messages which have been sent to it and are waiting to be processed. This queue is maintained as a list on the heap of each process. Having copied the message to the receiving process, we now link the message onto the end of this list. To facilitate this, each process either has 2 more registers. Message queue, this contains the head of the message queue. Last in message queue, this is a pointer to the last element in the message queue. This facilitates adding message to the end of the queue. When a message is delivered to a process, the receiving process is placed on the scheduler queue. Erlang implements active message reception in a manner similar to STL. When we receive a message, we try to match it against the alternatives in a receive statement. If there is no match, we retain the message on the message queue so that it may be processed later. Consider the following code fragments. This is compiled into the following code, so wait. Okay. Instruction 1 causes the process to be suspended if there are no messages awaiting reception. If there are one more messages, the first message is pushed onto the stack. The try me else chain used instruction 2 and 7 work in the same way as in the pattern matching of the heads of functions. Instruction 2 to 5 are used to match the tuple analyze number, and instruction 8 to 11 are used to match the tuple change number destination. If neither of these rules of these tuples match, the try me else chain causes a jump to instruction 13. This instruction saves the current message which did not match. Instruction 14 jump back to the start at instruction 1, either causing the process to be suspended if there are no more messages in the message queue, or pushing the next message in the message queue onto the stack. Okay. If we match one of the tuples, we execute a join save queue at 6 or 12. This instruction removes the message which match from the message queue and replaces any messages which were saved by instruction 13 into the message queue. So 6 and 12. Okay. To facilitate this, there is another register for each process. Save point. This register points to the next message in the message queue, which is a candidate for reception in the current message reception. In this way, we need not start matching from the beginning of the message queue every time a message is received. More advanced feature. Erlang also has facilities for registering processes, timeouts in message reception, and highly sophisticated mechanism for handling runtime errors. This also probably affects the virtual machine on the emulator. Discussion of this is beyond the scope of this paper. Compilation and linking. Erlang modules has a unit of compilation. Each module is compiled to instruction as described above. These instructions are then assembled, and an object code file is produced for each compiled module. Internal references within each module can be resolved at compile time. External references, like function in one module which call function in other module, are resolved at load time. Each Erlang module contains an export clause defining the function in the module which are accessible from outside the module. Consider, for example, the factorial function we examined previously. We see that the function factorial with one argument, if like factorial 1 is export from the module test. Within the module test, we can call factorial 1 with the argument 5. Simply by writing factorial 5, this will generate the instruction call local factorial 1, the address of which may be resolved at compile time. If we call factorial 1 from within another module, we must write this factorial 5. This says call factorial 1 in the module test. This will generate the instruction called remote test factorial 1. The address here can first be resolved at load time. To make this possible, the addresses of all exported functions are kept in export table. Each exported function is allocated a slot in this table either when the module exporting the function is loaded or when a module making a call to the function is loaded. The index of this slot is patched into the object code at load time. Calls to exported function are thus always made via this table. This means that the order in which modules are loaded is not important. It is also the basis for code replacement in a running system. Loading a new version of a module means that we can replace the addresses of function in the export table. New calls to function in the replaced module will thus use the new code. Okay. So this part here, I think it's quite important, in particular this part 1, because it explains how the Erlang virtual machine is dealing with code updates, and this is really nice. We have a table, we have different references, remote and local, and we can switch between them. Nice job. Last call optimization. Consider the following function which computes the sum of a list of integers. In the above, we cannot evaluate the plus until both its arguments are known. This means that we must compute sum t before we can return from the function. This in turn mean that we will not be able to compute the first term t before we get the end of the list. Okay, so the 0 because there is nothing in the list. Each call to sum t creates a new stack frame, like returning values on a command of the function. If the list is long, this will require a large stack. An alternative way to write the sum1 function is the classical call optimization. So we have an accumulator here and we put everything in the accumulator. In this version we introduce an accumulator set to 0 at the start and then passed as a parameter to sum2. The sum2 function now simply returns the result of the recursive sum th plus accumulator call. The Erlang compiler recognizes this and instead of using a call local sum2 uses enter local sum2 instruction. This instruction does not set up a new call frame on the stack, but overrides the current call frame. The function sum2 will not use up stack space. This optimization is called the last call optimization, since it is always the last call made by a function which can be treated in this way. It is vital that long-lived processes which are common in real-time systems are written this way. The following is an example of such a process. So we have a process with some data. We have the receive clause, we are waiting for messages. We have from info from ref query, data1 process info from blah blah, server data1, and we are looping it. And this is the same here. So if we are doing some query, we are processing the query, we are storing the reply directly in the reply variable, and we are sending the result to the process who requested this result. The process in the example above executes a loop which ends with a recursive call. Last call optimization applied to server data1 and server data ensures that the process will execute in a constant stack space. Garbage collection. Space on the stack on the heap are allocated sequentially. Call frames temporary variable are pushed onto the stack when function calls are made, or the stack space allocated by a function is reclaimed when the function returns. The space on the heap is not reclaimed until all the heap allocated to a process is used. At this time, many of the objects on the heap are probably no longer in use. They are not referenced. When the heap is full and we need more heap space, we call the garbage collector. The garbage collector is in fact not a garbage collector but a collector of valid data to which there are references. Before garbage collection, memory is allocated for a new heap. Starting from the top of the stack, we scan the stack looking for references to the heap. References objects are copied from the old heap to the new, and the references on the stack are adjusted to point to the new heap. When we have scanned the stack, the new heap may contain references to the old heap. We therefore scan the new heap looking for these references. When we find such references, we copy the object to which they point onto the end of the new heap and adjust the pointer on the new heap. Garbage collection is finished when we reach the end of the new heap. We can now free the memory allocated to the old heap. Okay, that's a bit complicated process, but if I correctly understand this part of of the text. First, this is not really a garbage collector, and we are only cleaning up all the invalid data. And this process looks like a little bit obscure to me because there is a lot of steps. This method of a garbage collection relies on the fact that there cannot be circular references on the heap since Erlang does not have destructive arguments. Since Erlang processes are small and garbage collection is done on a per process basis, the time for each garbage collection is very small. Dynamic resizing of processes. If when we have performed the garbage collection we still require more heap space, we allocate a bigger heap and call the garbage collector again so the old heap is copied to the bigger new heap. If we should require more stack space, we allocate memory for a bigger stack and copy the old stack. In the same way, if we find that the process has much more stack and heap space than it requires, we can shrink the stack and the heap. The size of an Erlang process does varies according to the space required. Typically, a process is created with 200 words of stack and 400 words of heaps. Dynamic resizing of processes is very useful in switching system application. For example, the subscriber line is usually inactive. Like in most cases, subscriber hopefully spend much more time not using the telephone than using it. A process representing a subscriber line is in Erlang just a few hundred words when the line is idle, but may expand to a few thousand words when the line is in use. In this way, we can make the Erlang process structure isomorphic to the concurrency inherent in the application without using an excessive amount of memory. Application. Our Erlang system has been installed in over 30 seats worldwide and has been used to control hardware in many different applications, including optical cross-connect system, switches for cordless technology, multimedia experiment and PABX system. Erlang has proved highly suitable for building a support system for Erlang. The compiler and debugger for Erlang has been written in Erlang. An interface to the X Windows system has been written and is widely used both in the Erlang support system and as command and simulation interfaces in various applications. Erlang object code is very compact. The basic Erlang operating system, including the compilers, the code loading systems, the interfaces to the file system, and to X Windows requires less than 60 kilobytes of object code. Under Unix, the process running this requires less than 2 megabytes of memory. The system has also proved highly portable. Versions of the system have been ported to VAX, MIPS processor, don't know if it's Motorola, but Sun and Spark CPU running various form of Unix onto a first CPU 30 processor running VxWorks. Measurements. The system described below were made using an Ericsson MD 110 PABX, which has been modified so that it can be controlled by a standard workstation, in our case the Sun Spark Station 2. A large prototyping experiment for a new PABX architecture resulted in a PABX control program with the following: basic cores and 10 features, both internal and over network, basic operator features, digital extension lines, operator lines, ISDN, trunk lines. The system also includes a sophisticated dynamic features loading mechanism in which telephony features may be loaded independently of each other. Little attempt was made to optimize this as regards execution efficiency. The system comprises about 25,000 lines of Erlang source code. Setting up a simple call requires 160 millisecond CPU time. A more simple demonstration system, which was made in conjunction with the ISS 90 conference, implements basic calls and 10 features: digital extension line, analog extension line. This system comprises about 5,000 lines of Erlang source code. Setting up a call requires 35 millisecond CPU time. Processes were used very freely in the above two systems. For example, each extension line is controlled by its own individual process, and each call in the system is controlled by two half-call processes. The telephone operating system, switch control, database, number analysis, and so on also comprise a multitude of processes. A very primitive system was designed with the objective of finding out how fast we could set up a telephone call. This system includes no features at all and comprises 2,500 lines of Erlang source code. Each call requires about 5 milliseconds CPU time. In all three cases, garbage collection accounts for about a quarter of the CPU time. This is much larger than in most applications in which Lisp or Prolog is used. This disparity is due to garbage collection in Erlang being done on a per process basis, and that processes in Erlang are kept small. In all three cases, a single processor was used. Erlang programs can be run in a distributed environment with little or no change to application programs. The capacity of the three systems above could thus be greatly increased by the use of more processors. Conclusion: there are many examples of how the use of declarative languages can reduce the workload required to implement large software systems by at least an order of magnitude. Experience of using Erlang has indicated that similar productivity gains can also be made in the sphere of real-time programming. Moreover, our implementation of Erlang shows that it is also possible to execute such software sufficiently efficiently to be used in commercially viable system. So we'll take a look at the references. Erlang, this one we already read it. Experiment with programming languages and techniques for telecommunication. So this one we didn't read it, but it's quite old. Armstrong, rapid prototyping. So this one we read it. I think it was one of the first one we read. An abstract prolog instruction set. Oh, this is Warren. So this is a Warren abstract machine. We didn't read it, but it's quite old and it's to describe how prolog is working. Recommendation: Z100 specification description language. Oh, I think we already take a look on that 2 weeks ago, I guess. The X Windows system, S intersection graphics, VxWorks programmer guide. Hmm, that's crazy. So we were able to run Erlang directly on VxWorks. Hmm. Crazy stuff. And a set of tools for VHDL design, logic programming in Paris. I don't know if you can have access to this one here. Let's try. In 1991. This is not the complete one. I think we will not be able to have it. We only have a small subset of it. Okay, so I think it's over for today. I have nothing to add because this paper is more about all the description of the feature at this time, so it was in 1992. Perhaps maybe 3 or 4 years after Erlang was released internally, and because the first release probably not the release but the first Erlang concept was made in 1986, so 6 years after they have a working language with a lot of custom instruction, a way to spawn process, small processes, toolbox debugging, graphical interfaces, and a lot of crazy stuff. So after 6 years you have something you can probably use, but this is not really, you don't have a lot of performance, you have a lot of performance issue. And I think the next paper will be mainly on optimizing this kind of things. And I already, we can see because actually everything I'm reading right now is directly coming from the awesome list I created and updated recently. I don't know if I can find it directly there. It doesn't, it's not the case, so this one here, and you have a list of papers you can check here, and there is no secrets. I'm just taking the oldest one and I'm reading them. So the next one is Carpe Diem, some implementation of Turbo Erlang. So here we are already talking about optimization, so 1 year after. And if I remember correctly, I already checked this one time just to have an idea of what Turbo Erlang was. And this is a really big paper, so I don't think I will be able to read it completely, but I think we will read at least half of this paper. But that could be also interesting stuff. Oh no, this is not a big one. We have 2 papers there. Maybe there is a problem somewhere. Okay, so only this part here, that's the one we're interested. So we will see that next time, and not next week, because next week it's open bar. I have a lot of information to share with you, and so we will see that later. So anyway, I think it's over for today. Have a great weekend and see you next week. Bye.